Hello students, welcome to EPG Pathshala. I am Dr. Amarjit Singh from Himachal Pradesh University, Shimla. Today we are going to discuss about module Crystalline Solids 2 from paper Solid State Physics. So students, let's see what we are going to learn in this module. So what are our learning objective of this module? So we have already defined Bravais lattices and classified materials in amorphous and crystalline. Now we will differentiate between 2-dimension and 3-dimension type of crystals, and we will learn more about Bravais lattice. And in this, one of the objective is also to learn about what packing fraction is, how to calculate the packing fraction. So packing fraction will let us know uh, how dense a particular material can be, and what are the structures which are the most closed pack, or what are the structures which are more loosely packed. So Bravais lattice in 2-dimension. So let us first talk about 2-dimension because it would be simpler. So as you understand, in 2 dimensions there are 2 vectors. You can define the 2 dimensions with 2 unit vectors, say namely A1 and A2, and there is an angle between these 2 unit vectors A and B. So with a different combination of A and B and gamma, question is how many kind of lattices we can produce, and that is of in 2 dimension there are 5 kind of such Bravais lattice we can produce in first, where so the first option is where you have both your unit vectors A1 and A2 of the same length and gamma is 90°, so that makes an square. The next, when angle between them is 90°, but A1 is not equal to A2, that means you make a rectangle. And centered rectangular lattice. So in the centered rectangular lattice, what we do is you have a rectangular lattice and you can put a lattice in between the center of this rectangle. So that is another type of a structure, which is another type of a rectangular lattice. So that's called centered rectangular lattice. In hexagonal lattice, here you have A1 and A2 which are equal, and the angle between them is 60°. If you make such a unit cell, you can basically produce a hexagonal structure in 2 dimension. And the fifth one, that is oblique rectangular lattice. So in this configuration, A1 is not equal to A2, and your gamma can be any angle, like it is not 60° or 90°, but it can be any other angle. So that now all these 5 type have included all the possibilities in 2 dimension. So there are 5 type of lattices, Bravais lattices, possible in 2 dimension. In this slide, this type of Bravais lattice in 2 dimension are illustrated. Bravais lattice in 2 dimension. So you can see that we have here drawn 5 kind of geometry. This on the left top it says a square lattice. So here our lattice vectors A and 2, they are perpendicular to each other and they are equal in magnitude. A1 is equal to A2. So that is shown, and this kind of lattice is called a square lattice. Now in another type where the angle between A1 and A2 remains 90°, but they are not same in magnitude when A1 is different from A2. So that's a rectangular lattice. So it depends, is the shape, actually the name of this lattice is the shape of this lattice. And now there is a centered rectangular lattice. So in this type of lattice, you can see that we have angle between A1 and A2 90 degree, where A1 is not equal to A2, but there is also a lattice point at the center of this rectangle. So that forms a centered rectangular lattice. In this fifth diagram, you see this is hexagonal lattice. So here A1 is equal to A2, and there is a specific angle of 60 degree. Then this is called hexagonal lattice. And in the next fifth one, here uh, it is a more general case where A1 is not equal to A2, and also the angle is not 60 degree, 120 degree or 90 degree, but anything. So this has to be an acute angle, but except 60 degree. So that forms this fifth type of lattice, that's called oblique rectangular lattice. So now I tell you a different kind of primitive cell, which is called Wigner seed cell. How to construct that cell? So now, as you can see in the figure, you have a lattice and you choose a point, and from that point connect the nearest neighbors with straight lines. As you can see in the figure, it is connecting with all its neighbors. And now in between uh, this 2 points, draw a perpendicular line. So in 2 dimension this would be a line, but in 3 dimension it would be a plane. And now you can see the shaded area in between. So that area is bound. Now this kind of cell, now you can see that it contains a single lattice point inside it, and the area which is enclosed by this cell is the smallest area. This type of construction is called Wigner seed cell. So the Wigner seed cell is always centered on a lattice point and incorporates the volume of space which is closest to the lattice point rather than to any other point. In this slide, we have illustrated the uh, Bravais lattice in 3 dimension. In 3 dimension, there are 14 type of Bravais lattices. 5 are shown on this slide, and then we will go over to the next slide. So cubic, for which A is equal to B is equal to C, alpha is equal to beta is equal to gamma is equal to 90 degree. So here all this 3 dimensions or 3 axes and 3 angles which are described, all 3 angles are equal and all 3 axes are equal. It consists of 3 non-equivalent space groups, lattice, simple cubic, body centered cubic and face centered cubic, and the geometry is shown on the right hand side. As you can see, that's a simple cubic which consists of atoms only at the corners, and body centered cubic, it contains an extra atom at the body center of this cube, and in the face centered structure the atoms are also there at each of these 6 faces of the cube. Now in tetragonal geometry, A is equal to B but not equal to C, and alpha is equal to beta is equal to gamma is equal to 90 degree. Encompasses the simple and body centered Bravais lattice. Now you can see that there are 2 structures here, that's a simple tetragonal and there is a body centered. Just like above, you can put one lattice in the center of the body of this simple tetragonal. So this is the continuation of this Bravais lattice in 3 dimension, and now the next class is orthorhombic. In orthorhombic, now you can see that none of this dimension is same. It means A is not equal to B is not equal to C, though alpha is equal to beta is equal to gamma is 90 degree. All angles are 90 degree, but all 3 axes are different. Like this is also shown in simple body centered base centered and face centered geometry. So there are 4 of this orthorhombic type. Now in the next class there is monoclinic. So in monoclinic geometry, A is not equal to B is not equal to C, though two angles alpha and gamma are 90°, but this angle beta is not 90° here. So you can see the geometry of this monoclinic structure, which is shown in simple monoclinic and body centered monoclinic. And now this the next structure is called rhombohedral, where A is equal to B is equal to C, alpha is equal to beta is equal to gamma, not equal to 90°. So here all angles are different, they are not 90°, excluding 90°. The difference between this and the simple one is that here, though all angles are equal, all axes are equal, but the angles are not 90°, they are oblique. The next structure is hexagonal, and here in hexagon, as you can see that A is not equal to B, A is equal to B, which is not equal to C. Alpha and beta, the two angles are 90°, and the third angle is of 120°. So this is a special structure. And this final one is triclinic, where A is not equal to B, not equal to C, and also none of the angles are equal and they are not equal to 90°. So these are the 14 type of Bravais lattice in 3 dimension. So now let us talk about an important parameter or of a crystalline material, that's called packing fraction. So packing fraction, as you can understand from the terminology itself, it tells you how much you can pack in a given volume. For example, if you, let us say, take a box of a carton and you starts to fill the sphere in that carton, what happen is that not entire volume is filled. In between these spherical balls, some volume will remain empty. So now if you try to fill it with, let us say, smaller balls, you will see that the empty space has reduced and now you can pack more material inside the cube. And for example, if you have to fill, let us say, sand, you can see that you can almost fill it completely, but sand grain also have a space between them, so some uh, uh, free volume remains there and it is not packing close to, let us say, complete packing. So there is always a free volume remaining due to the shape of the molecules which we are trying to fill in a given structure. So this packing fraction is basically all about how much mass you can fill in a given structure, that we will define in terms of formula in the next slide. So here we define a packing fraction. As you can see that on a slide there are 4 circles or spheres, one can say, they are touching each other and making the squares. There, if you touch their centers, connect their centers, they make an square. So the idea is the packing fraction is the volume of contributing spheres and the volume of a unit cell. Now you can see that inside the unit cell it is the entire sphere is not contained, but a large portion of this sphere is outside this square lattice. Only 1/4 of this circle is coming inside the cell. So from each corner a contribution of 1/4 is coming. So when you talk about a cubic structure, it has got 8 vertices, and from each vertex there is 1/8 of atom which is contributing to the volume of the unit cell, where you see that volume of spheres is equal to 8 multiplied by 1 upon 8. So this 1 upon 8 implies that only 1 upon 8th portion of this sphere is inside the unit cell, rest is outside. So that will be counted in the next cell. So that way the volume of the sphere is 4 upon 3 pi r cube, and its 1/8 volume is contributing to the unit cell, and there are 8 such corners. So that make up that volume of spheres. But if you calculate the volume of a cube, which is calculated on the top, which is 2r multiplied by 2r multiplied by 2r, 8r cube. So if you divide, you get 0.52. So this packing fraction is a unitless. It tells us that it is somewhat empty somewhere in between, so that this packing fraction is not 1. So packing fraction 1 means there is no empty space, just like you can see that in middle of this 4 circles there is an empty space here. So if the packing fraction is 1, that empty space will not be there. So here we have shown another example of calculating the packing fraction, and you can see the structure is BCC, body centered cubic. There is a cubic structure, and in the body center of this there is one atom, and parallel to this we have shown another structure where we have shown the model in which the atoms which are contained only the cube are represented. I mean, just like we cut the apples or pears and then fill them into the cube. So that's how it is represented on the left hand side. So the volume of the cube, it's simple because A multiplied by A by A. So this is unit, is the volume of the cube. Now we have to count that how many of these atoms or spheres are contained in these unit cells. So we can see that it is multiplied by 2 multiplied by 4 by 3 pi r cube. So there are 2 atoms. One atom is there at the center, which is completely inside the unit cell, and one atom is coming from 8 corners, 1/8 of each atom. So that makes us 2 atoms, and then we divide it by a volume of the unit cell. Here in this geometry, the volume of the unit cell is represented in terms of the radius of this sphere, where we have shown here in the equation below the relation between A and R. So we can talk about the volume of this cube in terms of R, so that we get a number. Finally, the idea is to get the number, and here the number is 0.68. So this structure is slightly higher dense as compared to earlier, or the packing fraction is larger. It contains large mass in a given volume. Now this is another example of calculating the packing fraction of FCC structure, that means face centered lattice. So I just would like to mention that here we see that at each faces there are 6 faces in this structure. So half of the atom is contributing from each face. So that makes 3 atoms coming from the face and 1 atom from the vertices. So there are basically 4 such spheres in this cubical volume, and when we divide the volume of spheres by the volume of the unit cells, we get the packing fraction, which is 0.74. So this is again higher than the earlier one, and this implies that this structure will possess the higher density. The relation between A and R due to the geometry is shown on the left hand side. Similarly, this is another type of a structure which is called HCP structure. So here also we do the same thing. We just find out that in this hexagonal unit cell how many atoms are there inside and the total volume of the hexagon. So there are 6 atoms which are contributing to this structure, and when we divide it by the total volume of the unit cell, we get the same packing fraction as we got in the earlier structure. Though these two structures FCC and HCP are different, but their packing fraction is same. It means both the structure contains same mass in a given volume. So here there is a table which shows that which lattice type it is: simple cubic, base centered cubic, uh, face centered cubic, or hexagonal closed pack. And these are the number of atoms per unit cell in the next column, and in the next column there is a packing fraction. So you can see that uh, the relation between number of atoms per unit cell and its packing fraction. So in simple cubic there is 1 atoms in a given cell, and the packing fraction is 0.52. It means it's almost half empty. In BCC you have 2 atoms per unit cell, and then the packing fraction increases. In FCC it is 4 atoms per unit cell and packing fraction is 0.74. And in HCP, though the number of unit cell is 6, but it has the same packing fraction. So the special thing about FCC and HCP structure is that they have same packing fraction, though their geometry is different, number of atoms per unit cells are also different. So in this slide we would like to compare the two structures. We have talked about FCC and HCP. They have same packing fraction, and how to construct these two structures using the sphere and stacking them. So the common thing about these two structures is the packing fraction. Now you can see that here is a diagram shown, and there are two type of voids between the atoms: vertex up B type and vertex down C type. The atom in the next layer sit on the B side. In FCC, atom in the third layer sit over the C side, and this repeats, giving rise to ABC, ABC, ABC type of stacking. It means you see here the A, then the next layer of atom will sit in the B, and the next layer of atoms then will go over to the C vertex. So that will make an FCC structure. In HCP, it is a repetition of AB, AB, AB type. In HCP system, it means hexagonal closed pack system, centers of the atom of the third layer lie directly over the center of the first layer, giving rise to AB, AB, AB type of stacking, as shown in the figure here diagram. So students, let's summarize what we have learned in this module. So first we talked about Bravais lattice in 2 dimension, and we learned that there are 5 different type of Bravais lattices which is possible in 2 dimension. When we go for 3D or 3 dimension, we extend one more dimension, then this Bravais lattice type are 14. So what is the meaning of this 5 and 14 here? So the question is, given the choice, these many types of lattices are possible, or this many type of particular shapes are possible in 2D and 3D. And so basically these a given shape, let us say cubic lattice in 3 dimension, it characterizes that which kind of symmetry group or symmetry operations is belongs to. So these are different classes of the crystals, we can say. And we also learned about the packing fraction. So packing fraction is a very important parameter which gives us information that how densely an structure can be packed. So there are different structures, let's say simple cubic, face centered cubic, body centered cubic, and we were able to calculate their packing fraction. So first, to get to the idea of packing fraction, let us take a very simple example. So let us take a box, a cubical box, and we have some spherical balls and try to fill that box with the balls. And definitely you will find that some of the space remains empty between the balls and not entire volume is used that way. Now second time you choose the size of the ball as smaller ones, and you can see that you could fill the more space this time, and the free volume, the voids still remains, but they are less as compared to the earlier one. In the next case, let us say you fill this box with the sand, and you see visibly it appears that okay, this is completely filled, but sand grains also have some size and dimension, and that will have a porosity that you can examine, because when you pour a water inside this, you can still go on filling the water inside the pores of a sand till you fill it completely. So packing fraction 1 means, let us say you fill it with the water so that a box is completely filled, so that is a packing fraction 1. The entire volume of this box is utilized in filling the material. So that is the idea of the packing fraction. As you can understand that these atoms and molecules, they have definite shape and dimensions, and due to this shape and dimensions we are not completely able to fill the entire space, or so to say some of the space is empty. We also learned that there are two structures which we call HCP and FCC, hexagonal closed pack structure, and FCC, face centered cubic structure. So these two structures have the same packing fraction, though they are two different kind of structures of unit cell, and these are, you can say, the highest packed structures. So there is an example that though you can have different structures, but their packing can be same. But this is not all to this crystal symmetry. There is a more to crystal symmetry that we will learn in point group symmetry and space group symmetry.